So you can skip to the 2-minute mark if you are really looking for a quick answer. In the following 30 seconds, I will tell you what to expect from this video. And in the next 90 seconds, I will tell you the background of my confusion about this topic. And after I tell you the answer of this question that you might have, stick around because I will explain what tensors and vectors really are in physics and how they are different from computer science. Wait for it, or skip to the 2-minute mark. So when I first heard about the word tensor, that was in first year, and it was supposed to be something very scary, higher mathematical thing, and it really isn't. I mean, I will show you, and you will quickly understand what a basic concept a tensor is. And you have been using tensors in ordinary life, and more so if you are into physics or engineering. um, and when I came to the field of machine learning, artificial intelligence, deep networks, deep learning, etc., the word tensor propped up again, and it was used in a completely different way. Google's library, famous library, is called TensorFlow, and I was like, is that the same tensor? Can anybody tell me? And the people who in my life who knew tensors very well, physicists and people who knew computer science, AI, ML very well, computer scientists, they were sort of independent Venn circles. So I didn't get an answer when I asked on my WhatsApp status. So that is why I'm here. I will tell you exactly what tensors are and exactly how computer science does not use the word properly. They misuse it. So let us wait for a few, maybe 4-6 seconds for the people who skip to the 2-minute mark. Okay, welcome people who skipped to the 2-minute mark. We were waiting for you. The answer is no, they're not the same things at all. In physics, we have vectors and tensors, and in computer science, what they actually call tensors are just multi-dimensional arrays or multi-dimensional matrices. Higher, like more than 2-dimensional, 3-dimensional, 4-dimensional matrices or arrays is what they call tensors. And when what they call vectors, it's just single dimensional arrays and of any arbitrary length. Wouldn't even call it dimension. And I will explain to you in the rest of the video why it is so, what makes a vector. If you have a vector which has, let us say, a person's name, age, salary, wife's middle name, whatever, that's not a vector, and why I'm not calling it a vector, and what is a vector, and all these questions I will tell you to begin with. What is a vector to begin with? That is what I will tell you. I'll try to keep this short, and it's very easy, don't worry. And if you're not getting something, then please hang around a bit. I will, in the end, I will always explain it. So today I weighed myself, and it came out to be 60.4 kilograms in the morning, and that's can't see the dot here, can you? So that's a tensor of rank 0. That's an example of tensor of rank 0. It's a number which is same in any direction. I could move in this direction, that direction, this direction, and it's the same mass. It's not weight, it's mass, and it's gonna be 60.4 kg. And now I'm going to tell you another set of numbers, and tensors are generalizations of numbers in higher sort of dimensions or collections, not dimensions exactly, ranks, and I'll explain what that means. So now we'll come to rank 1 tensor. Can you guess what it could be? After weighing myself, I went to a park on my bicycle, and if you wanted to measure my momentum, let's say my velocity, um, you could put it in a matrix like or array like this, where you have now to represent my speed, you necessarily, I mean not speed, velocity, you necessarily need all these three components. And why is that? What does this actually mean? This means that if you have x, y, and z, the z direction is coming out of the board here. So this means that I was going about 12 kilometers per hour in the 12.4 in the x direction and 5.8 in the y direction, and this was my total speed in the xy. And then there was maybe I was also going on a slope a little bit, so there was a little bit movement in the z direction, and that's 0.5, so that the vector would come out of the board a little bit like this. And you need these three independent directions because there is a force along this z direction, what we call gravity, and that really determines things. So you need, I mean, it does not act along these directions at all, it only acts along this direction. So it's important to have three independent quantities to represent my velocity. And this is a rank 1 tensor, and this is a generalization of a basic number which is the rank 0 tensor. It's a scalar, and then you have a vector um, which is, well, 3 dimensions. Now you may not probably guess what's coming next. We have rank 2 tensor. Keep in mind that these two are tensors, and what we will discuss is another tensor. And here, if you're talking about 3 dimensions like space, then we would have 9 components. Let us call it G11, G12, G13, G21, G22, G23, G31, G32, and G33. So what is this? So it's going to tell you information about two directions at once. So when you see G31, you can imagine it as GZX. So it tells you something about the direction Z and direction X. So if don't worry, I'll quickly tell you what use we could have with this. So a basic example we could have is when you have a Cartesian coordinate system where any point can be represented as a x, y, z, 3 coordinates, and what that really means is to get to that point you travel x in the x distance in the I direction, ith direction, along the direction of the ith basis vector. Then you travel y distance in the direction of the jth basis vector, and then you travel z distance along the kth basis vector. So this I, j and k are basis vectors. Let us denote them by a simple symbol, something like b a. No, can't be a. Let us say b alpha. So the vector b alpha is in this case a collection of 3 things: I, j, and k. The caps represent that their length is 1, but you could have a basis vector whose lengths are not 1, and which is very important. It's gonna come up. So now what you can store in this tensor here, what we would call a metric tensor, is the information about these basis vectors. So g alpha beta, so if alpha is 1 and beta is 2, then we have 1 2 g1 to this one will be equal to b alpha dot b beta. Now with alpha beta and damn it. Okay, so you know with the basic Cartesian orthonormal basis vectors that if you wanted to write this matrix, no, you can't see it, sorry. I will just tell you without changing anything. So G11 is the dot product of the ith vector with itself. So I dot I, that's 1. Then you have G22 is I dot k dot k, which is 1, and G33 is sorry j dot j, which is 1, and then k dot k, which is 1. And then G12 is the dot product of I and j, which is 0 because they are at 90° with each other. So you have all these values as 0 because that's how orthonormal basis sets work, that any dot product between the basis vectors is 0 except it's with themselves. So you would ask then, yeah, so you could guess that it would just look like a identity matrix. And you might ask, what's the use then of a metric tensor? The use is that you could move to a different basis here. Instead of using ijk, you could use something like 3i, then 2i plus 5k, and maybe just k plus I don't know. And it may or may not be a basis, because the criterion for deciding a basis is that none of the vectors should be able, like you should not be able to construct one of the vectors with any linear combination of the other two vectors. And I just wrote this down randomly and I haven't checked it, but let us assume that it's true for this case in particular. Wait, there is no j here, so let me put a j here. You're gonna need a j. um, so if you have a weird basis vector uh, basis system, basis vectors like this, then you are not going to have a identity matrix. For example, this first component g11 would be 9 because it's 3 square. Then g21, so multiplication of these two would actually be 0 in this case, but the multiplication of the, let us say 3 1 is going to be 3. So this matrix vector, let us just calculate this. It will be 9 0 3. I'll quickly calculate it. mm, that's that's going to be 4 plus 25, that's 29. And this is going to be 1 square plus 1 square, which is, well, just 2. And then here we will also have 3, and we are yet to calculate this value, which is the product of these two. So 2 plus 5, that's 7. So we'll have 7 here. Wait a minute, what? So you're going to have a weird metric tensor, and this metric tensor right here represents everything about this weird new uh, basis vectors that you have mentioned. So what really a tensor is, if I say Euclidean tensor, what it really is that it combine rank 2 tensor. It takes a combination of two vectors and then it represents a quality about them. In this case, it represents the scale and the angle. So these represent, like, the diagonal elements represent the scale of your coordinate system, and this represent the shear, like the angle between the um, basis vectors. And this comes really handy when you're discussing general relativity, where we realize that these are actually also dependent on the gravity, or like the strength of the gravity. If there is a very heavy object around you, then literally the lengths around you and the time durations are going to change. And it also depends on, if you're looking at someone else who is moving at different speed, then it's gonna look different to you. And that's where this comes in handy in physics. But the word tensor itself comes from a mechanical definition, mechanical engineering standpoint, where you have a cube, and the cube could be compressed in this direction, like this faces, like in the x direction, faces in the x direction could be compressed along the x directions. They could be sheared along the y directions or the z direction. So you would have a combination of all these three. It could be compressed, sheared this way and that way. So, and on all these three faces. So you need 9 quantities to represent what's happening to a cube. And you're not talking about a cube, you're talking about a miniature, like a hypothetical small cube inside a huge metal, so that you could do an analysis. And that's where the word tensor comes from. But it's a generalized form of a number, and you could go even higher. So when you go higher than this, than rank 2 tensor, you have rank 3 tensor, which is going to be a 3-dimensional matrix. And I mean, when I say dimension, you could go as small as 2 dimensions, and it would still be like a 2 by 2 by 2 cube. If you have 4 dimensions, like 3 space dimensions and 1 time dimension, it would be a 4 by 4 by 4 cube. But it would be a rank 3 tensor. This is also a tensor. Now let's come back to the computer science tensor. It's not a tensor. So what happened with computer scientists was, well, they decided to call something like a person's name, roll number, their wife's name, their father's, grandfather's name, whatever. Like they put this in a basic array. Uh, let me give you a better example. A customer's name, their salary, their credit score, and what debt they have, or whatever bank has information. Like you put this customer's vector, which is an array, in the neural network, and out pops maybe whether this customer is going to buy this platinum credit card or whatever. Like what's the probability that they would buy, and you should suggest them and spend energy trying to sell that to them. So this first vector array of things which are very different than each other is not a vector, because for something to be a vector, the elements of that vector have to be derived from the same scalar field. Like here they're all kilometers per hour, they're all speeds, and you're not doing that with vectors of, let us say, what I just described, information about a customer of a bank. And you would ask, what change difference does it make? You add one customer to another customer, and maybe you can add salary with salary, and you could add credit score with credit score. Or maybe a simpler example, I have a bag of fruits, and there are 3 tomatoes and 3 strawberries and 5 bananas, and I have another bag which has 5 tomatoes and 8 strawberries and 3 bananas, and you add these 2 bags up, and then bananas get added with bananas and strawberries with strawberries, and tomatoes with tomatoes. So isn't that a vector? Because you're adding, like, there are independent directions and you're adding them uh, element by element. No, because vector has another rule, that it needs to stay invariant. Tensors in general have a rule that they need to stay invariant under transformations. So this speed right here is a physical quantity. It's not going to change if I rotated my axis a little bit. If I said that the ground is the up direction and the sky is the down direction, or if I just change the x and y to just whatever, east to west, I turned the x from east to north, and suddenly all the components here will change, but the velocity remains the same. That's the core concept behind what a tensor really is. It doesn't change when you transform the coordinates. The coordinates change, and very predictable. You can calculate what the new coordinates would be, but the tensor doesn't change. Now it is meaningless to think about a transformation like rotation on an array about employee information. What does it mean to rotate it? I mean, here when you rotate it, some of this goes here, some of this goes here, and that's meaningless when you are thinking about a vector in computer science. And about tensors, what happened was you get a lot of multidimensional structures, multidimensional data structures in um, uh, neural networks, and in general machine learning, etc. Like even for simple things like optical character recognition, you have 5 dimensional matrices. And when you have 5 dimensional matrices, I don't know, somewhere someone in the world decided that those are not matrices, those are tensors, because maybe they took a the physics 2 course back in their undergrad in their first year. Actually, in the US they teach like everything very late. So maybe it was even the third year when they heard the word tensor, or even learned the tensor. I mean, in first year itself we are taught tensors in the electrodynamics course. Um, so yeah, basically they are not tensors in computer science, they are multi-dimensional matrices. And now what's the difference between a matrix and a tensor? Here this is a tensor contained in a matrix, like the body of the tensor is like it's inhabiting a matrix, but not every matrix is a tensor. um, Not every array is a vector. I mean, a vector is a tensor also, rank 0 tensor, but we just prefer calling it a vector. So that is the story. I hope it helped. 19 minutes. How many of you are watching, really? If you're watching, maybe write tomato, tomatoes, strawberries and bananas in the comments, like any of these 3 fruits that you like. Tomatoes are fruits. So let's end at 20 minutes because that really seems proper. I mean, odd number of minutes seems wrong. There was a little bit of delay when I started this